Hello and welcome to the video lecture on elimination reaction. Today we are going to talk about the effect of leaving group on E2 reaction, and then we are going to move on to the stereoselectivity of E2 reactions. Effect of leaving group is an important factor that controls the rate of elimination reactions. When we have better leaving groups, we have high rate for bimolecular eliminations. As the leaving group ability of the X improves, the rate of E2 reaction increases. This is an expected outcome because alpha কার্বনের সাথে X এর যে বন্ড আছে সেটা বাইমলিকুলার এলিমিনেশনে ডিটারমিনিং স্টেপে ভেঙে যায়। অতএব যদি X এর সাথে বন্ডটা তাড়াতাড়ি ভাঙে, কার্বনের বন্ডটা তাড়াতাড়ি ভাঙে, তাহলে রেট অফ দ্য রিয়াকশন ইমপ্রুভ করে। তো তাহলে আগে জানতে হবে যে গুড লিভিং গ্রুপ কারা। গুড লিভিং গ্রুপ তারাই যেখানে CX বন্ডটা ভাঙতে কম এনার্জি লাগে, অর্থাৎ one of the factors among many which control the leaving group ability of X or X minus is the bond dissociation energy of the CX bond. যখন CX bond ভাঙবে তখন X minus মিডিয়ামে বেরিয়ে আসবে, and therefore the stability of the X minus, that is the ability of the X to handle the negative charge or the excess electron density, is important in considering the leaving group ability of the X minus. যত উইকার হবে CX বন্ডটা তত সেটা বেটার লিভিং গ্রুপ হবে এবং তত রেট অফ bimolecular elimination ইমপ্রুভ করবে। And that is why for halides we have this observation যে for organoiodides the rate is fastest, for organofluorides the rate is slowest, because কার্বনের সাথে আয়োডিনের অরবিটাল সাইজ মিসম্যাচের জন্য CI bond dissociation energy is very low. On the other hand, orbital matching এর জন্য কার্বনের সাথে ফ্লুরিনের অরবিটাল ম্যাচিং এর জন্য the CF bond energy is one of the strongest bond known, and therefore it is very difficult to break. In addition, as X minus becomes a weaker base, that is, it handles the negative charge better, it becomes a more effective leaving group. A stronger base is a poor leaving group because it is not comfortable with its negative charge, and therefore it seeks to react with any sort of electrophile that it can get its hand upon, such as proton or electrophilic carbon, etc. And therefore it does not want to leave the carbon to which it is attached. It wants to cling on to, আঁকড়ে ধরে থাকে যে কার্বনটার সঙ্গে ও অ্যাটাচড হয়ে বসে আছে এবং নিজে X মাইনাস হয়ে বেরোতে চায় না। This is, in other words, telling you that X minus is a very bad leaving, and therefore you can get a quantitative as well as qualitative measure of leaving group ability by looking at the basicity of the X minus. And we already know that to judge the basicity of X minus, it is better to consider the acidity of the corresponding conjugate acid. So if the pKa value of HX is very low, then it is a strong acid, X minus is a weak base, and consequently X minus would be a good leaving group. So আমাদের যে আগে আমরা যেটা দেখলাম যে iodide is a better leaving group than fluoride, if we take into account the acidity of the HI, pKa of which is -10, and compare that with the pKa of the conjugate acid of fluoride, HF, which is 3.2, then also we arrive at the same conclusion that iodide is a better leaving group compared to fluoride. And the leaving group যার conjugate acid এর যেটা আমরা এইমাত্র বললাম pKa লোয়ার হবে সেটা বেটার লিভিং গ্রুপ হবে, আর যার কনজুগেট অ্যাসিডের pKa রিলেটিভলি হায়ার হবে সেটা রিলেটিভলি পুয়ার লিভিং গ্রুপ হবে। A case in point is case of the alcohols. You do not get elimination reaction on alcohols because OH minus is a strong base. The corresponding conjugate acid is water, and that is pKa being around 15.7. It's not a very strong acid, therefore hydroxide is a relatively strong base, and therefore hydroxide is a bad leaving group. you have to make the OH leave from the molecule by converting it to something different. Now, this is one fact. These are one factor for one aspect of the leaving group ability. But perhaps the more interesting aspect is the change of regioselectivity when you change the leaving group. What do we mean by regioselectivity change? That means if I have a organohalide or some substrate from which the elimination reaction is happening, and we have two different types of beta carbon from which the protons can be abstracted. One leads to the formation of the more substituted alkene, the other leads to the formation of less substituted alkene. Then the more substituted alkene, as we know, is called the Zaitsev product, and the less substituted alkene is called the Hofmann product. And you have this scenario যেখানে আমরা এখানে একটা এক্সাম্পল নিয়েছি একটা 2 halo hexane, and we are treating that with sodium ethoxide in ethanol. So এটা একটা 2 alkene তৈরি করছে আর একটা 1 alkene তৈরি করছে. This 2 alkene is uh, uh, being produced in two different diastereoisomers. One is the E diastereoisomer, the other is the Z1. But overall আমরা এটাকে 2 alkeneর পপুলেশনের মধ্যেই ধরছি. When we have X is equal to iodine, then the ratio of the Zaitsev and Hofmann product is 80:20 approximately, and it is expected. We have already rationalized why the Zaitsev product dominates in this case. But as you change the leaving group from iodide to bromide to chloride to fluoride, the percentage of the Zaitsev product slowly decreases, and the percentage of the Hofmann product, that is the less substituted alkene, slowly increases. So much so that when you arrive at fluoride, the Zaitsev product is the minor product and the Hofmann product is the major product. So with organofluorides, it is generally observed that Hofmann product tends to dominate the product mixture. And not only that, the same trend is observed for the onium ions. That is, if we have a quaternary nitrogen or a sulfonium ion, an ammonium or a sulfonium ion here, then also we can see that it is the less substituted alkene which is, dominates the reaction mixture. That is, Hofmann product is the major product. So, say for example, in this system where you have the possibility of formation of 2 pentene and 1 pentene, it is 1 pentene which dominates. The next one is even more interesting. You can abstract this beta proton, which is obviously a secondary carbon. You can abstract this beta proton, which is obviously a primary carbon. So abstraction of beta proton from beta prime will give you ethylene plus this tertiary amine, and abstraction of the proton from this blue beta side will give you propene and this tertiary. It is the less substituted ethylene which dominates the reaction mixture, not the more substituted propene. So again, we are saying that Hofmann product dominates. We have already explained, as we have told you, that why Zaitsev product is favored for E2 reaction when the leaving group is iodide, bromide, chloride. Well, that is because in the transition state, the partly formed double bond is, when it is more substituted, the transition state is more stable. Because in that case, we were considering that the transition states were like alkenes. But we need to now explain that why changing the leaving group from iodide to fluoride, and particularly for onium ions, why the regioselectivity favors the Hofmann products. Again, clearly we have to invoke the transition state argument. Recall from our previous discussions as that the cleavage of the CX and the CH bond, although it happens in E2 reaction in a one single step, they could be synchronous. That means C beta hydrogen bond making at extent এবং C alpha X bond making at extent, they could be equal, or there could be two other scenarios, in one case the C beta hydrogen bond breaking that exceeds the extent of the C alpha X bond breaking. In that case, there is a development of del negative charge on the beta carbon, and that TS actually resembles more of a carbanion, less of an alkene. And the other scenario is that the extent of C beta hydrogen bond breaking and the extent of C alpha C alpha X bond breaking, they are not similar, and the C beta hydrogen bond breaks less than the C alpha X bond breaks. Therefore, in that case, there is a development of a partial positive charge on the alpha carbon, and that electron deficiency leads to a transition state which is like more like a carbocation, less like an alkene. So ideal E2 transition state এর বাইরেও আরো অনেক রকম possibilities we can encounter. We have already talked about it. Now think what is happening with living groups, special living groups like fluoride or onium ions. When the living group is highly electronegative, like when you have a sulfur plus or a nitrogen plus or a fluoride, then two things happen. Generally, two things happen. One is that any sort of beta hydrogen that you have in the substrate becomes highly acidic because তার পাশের কার্বন আলফা কার্বন সেখানে একটা strongly electron withdrawing group রয়েছে, and all these sulfonium, ammonium or fluorine, they have strong bonds, relatively large CX bond dissociation energies, and therefore these transition states are like less like alkenes and more like carbanions, as we have told you, as the C beta hydrogen breaks very easily because it is acidic, but because the CX bond is strong, the CX does not break that much in the transition state. So in the transition state, there is a development of the negative charge onto the carbon, which is beta, and therefore we can consider these transition states as a carbanion. Now, if we concede that we have transition states which resemble more like carbanions, less like alkenes in this case, then it is conceivable যে সেই বিটা হাইড্রোজেনটাই খাবে যে বিটা হাইড্রোজেনটাকে খেলে কার্বনায়ন লাইক টিএসটা মোর স্টেবল। সো লেট আস কনসিডার আমাদের এক্সাম্পলটা দেখা যায়। আমাদের এখানে এই বিটা কার্বন থেকে প্রোটন খেতে পারে বা এই বিটা কার্বন থেকে প্রোটন খেতে পারে। ইফ দে অ্যাবস্ট্রাক্ট দ্য ব্লু হাইড্রোজেন, then I will get two alkene, but if the red hydrogen is abstracted, I will get the one alkene. So draw the transition states. We have a del negative charge here in this case, and we have a del negative charge on the less substituted carbon here. And because this alkyl group imparts a plus I effect on this secondary carbon, the hydrogen is relatively less acidic. তার কারণ অ্যাসিডিটি ইনফ্যাক্ট ডিক্রিজ করে যদি সেই সেন্টারের সঙ্গে তুমি ইলেকট্রন ডেন্সিটি বাড়িয়ে দেয় এরকম ইলেকট্রন রিলিজিং গ্রুপ রেখে দাও, আর অ্যাসিডিটি ইনক্রিজ করে যদি তুমি সেখানে একটা ইলেকট্রন উইথড্রয়িং গ্রুপ রেখে দাও। তো এই সেন্টারের ওপরে কোনো ইলেকট্রন ডোনেটিং গ্রুপ নেই, বাট এই সেন্টারের ওপরে দেয়ার ইজ অ্যান অ্যালকিল গ্রুপ হুইচ ইজ ইনক্রিজিং দি ইলেকট্রন ডেন্সিটি, and therefore this blue hydrogen is relatively less acidic, the red hydrogen is relatively more acidic. So ethoxide will have greater tendency to abstract this proton. Not only that, if you consider the transition state, then the secondary carbon, when there is a del negative charge on the secondary carbon, it is in fact destabilized by the same alkyl group, which reduces the acidity of the blue hydrogen because it is destabilizing the potential build-up of the negative charge here due to its electron releasing nature. এখানে এই ধরনের কোনো destabilizing feature নেই, although the partly formed double bond is more substituted here and it is less substituted here. That factor which was controlling the regioselectivity and favoring the side-step product when the living group was bromide or iodide, that factor is a minor factor here. The major factor is that because the transition state is not like an alkene but like a carbanion, it gives rise to the two alkene as the minor product and one alkene as the major product. This argument or this observation is actually a corroboration of the transition state argument. কারণ আমরা এর আগেও বলেছিলাম যে E2 reaction there is a tendency to rationalize the outcome of the regioselectivity outcome of E2 reactions by saying the more substituted alkene more stable, and that is why it forms faster. But we told you that it's not like that. It is the transition state that controls the rate of the reaction, and this is a clear-cut vindication of that theory, because otherwise you cannot possibly explain that why for fluorine or for quaternary ammonium or sulfonium salts the less substituted alkene is the major product, because this is always thermodynamically less stable compared to the two alkene. Therefore, if this is true that Zaitsev product dominates the reaction mixture because it is more stable, then the Zaitsev product should always be the major product. But as you can see, if you change the leaving group to these special leaving groups from fluoride, from bromide to fluoride or something like that, then Zaitsev product can even become the minor product. Okay, and the acidity of the hydrogen, that also obviously matters. The the This one is one particular example when you have possible abstraction of a benzylic hydrogen and a primary hydrogen. If you abstract the primary hydrogen, you get ethylene, less substituted compound, and uh, if you abstract the benzylic hydrogen, you get styrene, which is the more substituted compound. So you can call this the Zaitsev product, you can call this the Hofmann product. But this time, you can see it is the Hofmann product which is the minor. That means the transition state for the abstraction of this hydrogen is actually more stable than the transition state for abstraction of that hydrogen. So why is that? When you abstract the blue hydrogen, the buildup of negative charge on the benzylic carbon gains stability from the conjugative influence, that is electron withdrawing influence of the phenyl ring. Remember, this is an sp2 carbon, so it exerts a minus I effect, as well as there are minus R effect that can operate. So if you are building up some negative charge here, then this phenyl ring can very much stabilize it. Not only that, we told you that this alkene character is less, carbanion character is more, but that does not mean the alkene character একদম নেই। এই জায়গাটাতে যে partially formed double bond আছে, that will be in conjugation with the phenyl ring. Therefore, this partially formed double bond will be like a bit more stable compared to a situation when you are abstracting the red hydrogen, and that red hydrogen being abstracted, you are forming this particular bond where, you know, you have absolutely no chance of getting any stabilization from the phenyl ring. Neither can the del negative get any respite. এর ইলেকট্রন উইথড্রয়িং ইনফ্লুয়েন্সের জন্য একে স্টেবিলাইজ করার কোনো চান্স নেই, nor this carbon partly formed carbon carbon double bond is conjugated with this phenyl ring. Therefore, abstraction of the red hydrogen, which is obviously less acidic because the blue hydrogen being benzylic is more acidic, negative charge will be like more stable here compared to here. We get the Zaitsev product as the major product. So it's not very wise to directly jump the gun and conclude that okay, this is a ammonium salt and therefore we will always have this kind of situation যেখানে Zaitsev product would be the major product or Hofmann product would be the major product. You need to consider the cases carefully and then decide যে ঠিক exactly কি হতে চলেছে. Hofmann product would be the major product, but it may turn out that the Zaitsev product could be the major product as well if the transition state is more stable. Now, before the advent of spectroscopic techniques, organic chemists used to do all sorts of reactions to understand the structure of their compound of interest. One such technique was Hofmann's exhaustive methylation, which was used to determine the structure of saturated heterocyclic compounds, which are found in alkaloids or natural products. তো সেটার ফিলোসফিটা ছিল এরকম যে you take the heterocyclic compound, a nitrogen compound like a 6-member ring I have taken here. It is a saturated pyridine system, and you methylate it. as much methylation as you can do. Obviously নাইট্রোজেনের উপরে তুমি এখানে দুটো মিথাইল ঢোকাতে পারো এবং কোয়াটার্নারি অ্যামোনিয়াম সল্ট তাহলে তৈরি হবে. Of course you are using methyl iodide, so you will have an iodide counter ion, and then you treat with moist silver oxide and then you heat it. Then the iodide is exchanged with hydroxide, and this hydroxide is capable of abstracting beta proton and give rise to alkenes. So যখন হাইড্রোক্সাইড এসছে, this is a very strong base here because there is no covalency between the OH minus and the positive charge center, so it's a free ion, and therefore it can abstract either this beta hydrogen or that beta hydrogen or that beta hydrogen. These are the secondary beta hydrogens, this is primary beta hydrogen, so that's the more acidic hydrogen. So we know that negative charge would be, you know, like more stable here in the transition state. The developing negative charge would be more stable here, and because this is a quaternary ammonium thing, the transition state will be like more like carbon ion, less like alkene. তো এই জায়গাতে নেগেটিভ চার্জ বা এই জায়গাতে নেগেটিভ চার্জ যত ভালো স্টেবিলাইজড হবে না, এখানে স্টেবিলাইজড হবে, তো তাহলে ও এই প্রোটনটাকে খেয়ে এই জিনিসটা দিল, এই অ্যালকিনটা দিল. We still have one nitrogen attached to the carbon, so we can again do the second cycle of Hofmann exhaustive methylation. So আরেকবার মিথাইলেট করলে এখানটায় NMe3+ হয়ে যাবে, and this time there is only one beta hydrogen that can be abstracted after you exchange iodide with hydroxide. This hydrogen is abstracted and we get a 1, 2, 3, 4, 5, 6, that means 1, 5 hexadiene. And then you notice that NMe3 has come out in the reaction medium, and then you think that from which saturated acyclic compound we could get this one. So we think back in this way and ultimately arrive at the starting material. But that is a thinking process. After doing the experiment, checking the intermediate this compound, checking the final alkene and the amine that is being released, we can arrive at this structure. If we have two isomeric heterocycles, nitrogen-based heterocycles, then doing the same Hofmann exhaustive methylation reaction may give rise to two different alkenes. যেমন আমরা যদি 3-methyl pyrrolidine নিয়ে শুরু করি, তাহলে Hofmann exhaustive methylation করলে quaternary ammonium stage এ যখন পৌঁছেছি, this is the tertiary hydrogen which is less acidic, this is the secondary hydrogen which is more acidic. তো বিটা হাইড্রোজেন এরকম দুটো আছে, তার মধ্যে এইখানে এইটাকে যদি খায় তাহলে এইখানটায় নেগেটিভ চার্জ আসবে which is more stable in the transition state compared to এইখানটায় নেগেটিভ চার্জ আসবে because এখানে মিথাইল ওকে ডিস্টেবিলাইজ করে দেবে. So this hydrogen will be preferentially abstracted and I will have a carbon-carbon double bond here. And then again do the same thing, and this time there is only one possible site from which the beta hydrogen can be abstracted, and then you heat it, then you get the isoprene derivative. So from 3-methyl pyrrolidine you get isoprene. From 2-methyl pyrrolidine you do the same thing again. So this is a less acidic secondary beta hydrogen, that is a less acidic secondary beta hydrogen, but that is the more acidic primary beta hydrogen because this is primary. এখানটায় negative charge, এখানে negative charge restable, এইখানে negative charge transition state will be like relatively more stable. Therefore this is the site from which the elimination will now take place. So we will get this intermediate alkene, which on again another cycle of Hofmann exhaustive methylation, the only possible beta hydrogen is here, therefore I will get a penta 1,4-diene. So from 3-methyl pyrrolidine I am getting isoprene, from 2-methyl pyrrolidine I am getting penta 1,4-diene. এরকম কোশ্চেন কখনো আমি দেখিনি যেখানে অ্যালকিন বলে দিয়েছে এবং অ্যামিন কি কোনটা বেরোচ্ছে সেটা বলে দিয়েছে, and then they have asked you to find out the structure of the starting heterocyclic compound, but যেটা দেয় সেটা হচ্ছে এই ধরনের একটা কম্পাউন্ড দিয়ে সেটার হফম্যান এক্সস্টিভ মিথাইলেশন করতে বলে, অর্থাৎ অন্তত গোটা 2-3 সাইকেল করতে বলে। তো সেই সাইকেল করার পর তারপরে কি অ্যালকিন তৈরি হচ্ছে সেটা পুরোটা ফুল এক্সপ্লেন করতে বলে, এবং সেক্ষেত্রে তোমাকে ইন্টারমিডিয়েট কম্পাউন্ডসগুলো দেখিয়ে কোন হাইড্রোজেনটা আগে খাচ্ছে, কোন হাইড্রোজেনটা পরে খাচ্ছে এবং কেন খাচ্ছে সেগুলো নিয়ে ইউ হ্যাভ টু টক আ লিটল বিট. Now let us go on to another aspect of elimination reaction, that is the stereoselectivity. That is the stereochemical outcome of E2 reaction. For example, if I am considering E2 reaction, sodium ethoxide induced E2 reaction on 2-bromopentane, then the regiochemistry is obviously not an issue, because with respect to this alpha carbon, these two carbons are the beta carbons and they are equivalent. So I have a E2 pentene and a Z2 pentene that could form by abstraction of hydrogen from this side. I could abstract the hydrogens from that side, but that is equivalent, so it's meaningless to do that. But if I am to abstract this hydrogen, I will get two different products. One is the E2 pentene, the other is the Z2 pentene. This situation we have already encountered, but at that point of time we did not discuss that. But it is now time for these to discuss why this E2 pentene diastereoisomer is the major product. These reactions are called stereoselective reactions, which means that they are resulting in the preferential formation of one stereoisomer over another. In this case, the E alkene is forming in preference with the Z alkene. And stereoselective reactions, they could be of like two types. One is that enantioselective, where two different enantiomers are forming, but one enantiomer is forming in preference over the other. In that case, that is an enantioselective reaction. But this is a reaction where one diastereoisomer is forming in preference over the other, and that therefore it is called a diastereoselective reaction. And this type of stereoselectivity is called the diastereoselectivity. So when you have base-induced dehydrobromination of 3-bromopentane, it is a diastereoselective E2 reaction, and we need to explain why this diastereoselectivity is coming. But before that, we need to understand one thing, that for a E2 reaction to happen, the primary requirement is that we should have a leaving group on alpha carbon and at least one hydrogen on beta carbon, and that hydrogen has to be abstracted simultaneously with the breakage of the CX bond. But এই যে তুমি কথাটা বলছো যে বিটা হাইড্রোজেন থাকতে হবে, it is not the only requirement যে বিটা হাইড্রোজেন থাকলেই E2 reaction হবে, সেটা কিন্তু হবে না. There is a specific conformational relationship between the C beta hydrogen and the C alpha X bond that has to be maintained in the substrate for the E2 reaction to occur successfully. What kind of conformational relationship? These bonds, that is the CX bond and the CH bond, and actually more precisely the C alpha atom, the C beta atom, the hydrogen attached to C beta, and the X leaving group attached to C alpha. All these four atoms have to be coplanar with each other, which is another way of saying that the CH and CX bond has to be on the same plane. Why do you need such a peculiar requirement? That is because in the transition state of an E2 reaction, you are forming a pi bond between the C alpha and C beta, and the pi bond is comprised of two p orbitals that has to overlap sideways. Therefore, in the transition state, the developing p orbital on the alpha carbon here and the developing p orbital on the beta carbon here, they should be in such a orientation that they are capable of forming the partly formed pi bond. In order to achieve this kind of orbital overlap, of course, the CH bond and the CX bond, they have to be coplanar with each other. If they are not coplanar with each other, then the developing p orbital on the alpha carbon and the developing p orbital on the beta carbon, they will not be parallel to each other, and therefore they won't be able to form the partly formed double bond in the transition state. And therefore, the two carbon atoms, the hydrogen and the leaving group, all of them have to be in the same plane. This is actually a stereoelectronic requirement. By stereoelectronic, we mean that a spatial relationship, that is a relative alignment of the orbitals involved in the reaction. And just as the the SN2 reaction has this requirement, peculiar requirement of the nucleophile approaching from the side opposite to where the leaving group is, that is the backside attack. So this stereoelectronic requirement that the hydrogen, C beta, C alpha and X, all of them have to remain in the same plane. This is a stereoelectronic requirement for the E2 reaction, because this particular bond, the CsP3 hydrogen 1s bond that is going to be converted into the transition state partly formed by p orbital. This CsP3 xsp3 sigma, that is this CX bond, this orbital system is going to be converted into the partly forming p orbital. This x will leave with its electron pair, but the sp3 hybrid orbital that the carbon was using to form the CX bond, that will turn into a p orbital. This sp3 hybrid orbital that carbon was using to form the bond with hydrogen, that will turn into a p orbital. So these p orbitals must be coplanar. They must be parallel to each other, and therefore this makes sense that hydrogen C bond and XC bond, they have to be coplanar as well to begin with. In terms of molecular orbital, you can explain that when E2 reaction is happening, the base from its highest occupied molecular orbital donates electron pair onto the CH sigma star orbital. The CH sigma star orbital electron dile the CH sigma bond will break. You already had some electrons here because CH sigma bond ekhane ache. So that electron pair from CH sigma bond, that will be transferred into the CX sigma star orbital, and that CX sigma star orbital electron donation er phole X will leave with the bonding pair of electrons, and then the carbon-carbon double bond formation will be like complete. This donation of the electron pair from base to the CH sigma star breaks the CH bond, and that donation from the CH sigma to CX sigma star breaks the CX bond, and ultimately we have this carbon-carbon double bond. So essentially, this is an orbital overlap between the CH electron transfer from the C beta hydrogen sigma bond onto the C alpha X sigma star. So that is only possible, that donation, this electron density transfer is only possible if the CH and CX are coplanar. Now there are actually two ways in which you can make this CH and CX coplanar. One is this arrangement where you have this anti kind of arrangement where CH and CX, they have this dihedral angle 180 degrees, as you can see from the Newman projection formula. Or you can have the CH and CX eclipse to each other. As you can see from the Newman projection formula, the dihedral angle is 0 or very close to 0. So either the anti form or from the syn form, this stereoelectronic requirement can be met. The CH or CX এক প্লেনে থাকবে. But if you look at these two arrangements, then immediately you are seeing that because of the unfavorable eclipsing interactions, the torsional strain and the van der Waals strain that destabilize this particular conformation, whereas the antiform does not have that kind of a problem. Eclipsing form to molecule থাকে না unless it is forced to exist in such a way. ও থাকে সব সময় কোনো একটা staggered form. So antiform being one of the staggered form is definitely much more stable than the syn form. And if you take a view from MO, then the sigma CH is like that, whereas sigma star CX is like that. If you have the anti-orientation, then the orbitals which are supposed to overlap, they have a size matching. On the other hand, if you have the syn orientation, then the orbital overlap is kind of compromised because this orbital size and that orbital size, that does not match. So we know that orbital size is an important factor when considering orbital overlap, along with relative orientation of the two overlapping orbitals and energies of the two orbitals. So যদি orbital size যেখানে ম্যাচ করে তাহলে সেখানটাতে ওভারল্যাপটা বেটার হয়। তো সেই দিক থেকে দেখতে গেলেও কিন্তু আমাদের অ্যান্টি ফর্মের ডমিনেন্স থাকবে কম্পেয়ার টু সিন ফর্ম। সো we are not trying to say that syn periplanar form এটাকে আমরা anti periplanar বলি, এটাকে আমরা syn periplanar বলি, as you know from the Klein-Prelog terminology that you have learned in your previous semester, or no in this semester. এই সেমিস্টারেই তোমরা কনফার্মেশনে যখন যাবে তখন তোমরা Klein-Prelog terminology শিখবে। সো এই অ্যান্টি পেরিপ্লেনার কনফরমেশন যদি অ্যাক্সেস করতে পারে তাহলে রিয়াকশনটা সেখান থেকেই হবে, বাট ইফ দ্য মলিকিউল ক্যান নট অ্যাক্সেস দি অ্যান্টি পেরিপ্লেনার ফর্ম then but can access the syn periplanar form, then only the reaction can happen from syn periplanar. So E2 রিয়াকশনের জন্য আগে দেখতে হবে যে অ্যান্টি পেরিপ্লেনার ফর্ম অ্যাক্সেস করতে পারছে কিনা, যদি অ্যাক্সেস করতে পারে তাহলে রিয়াকশন হবে, আর যদি অ্যাক্সেস করতে না পারে তাহলে সিন পেরিপ্লেনার যদি অ্যাক্সেস করতে পারে তাহলে রিয়াকশন হবে। যদি এই দুটোর মধ্যে কোনোটাকেই অ্যাক্সেস করতে না পারে, ইফ দ্য মলিকিউল ক্যান নট অ্যাক্সেস এনি ওয়ান অফ দিস টু অপশনস, then bimolecular reaction will not take place. Say for example, we have a bicyclic system where the halogen uh, is at the bridgehead position. Now, do we have beta hydrogens? Of course, we have beta hydrogens. We have beta hydrogens here. We have beta hydrogens here. These two positions are equivalent, and then we have the second type of beta hydrogen here. This molecule cannot undergo unimolecular elimination. That is because that requires formation of a carbocation, and if you make this bond cleave and generate a carbocation at this bridgehead position, then it is very difficult to form this type of carbocation because it is not planar, and therefore consequently it is very high in energy, and the activation energy for its formation is very high. So a E1 reaction is out of the question. But this molecule, despite possessing lots of beta hydrogen, cannot even undergo E2 reaction. Why? That is because neither of these hydrogens, neither this one nor that one nor that one nor that one, you can see neither of them are either syn periplanar or anti-periplanar with this chlorine. With this chlorine, this hydrogen is almost like orthogonal. With this chlorine, these hydrogens are not syn periplanar or anti-periplanar. Neither this hydrogen is syn or anti-periplanar. Therefore, this chlorine, carbon-chlorine bond, has lots of beta hydrogen, but not the stereoelectronic requirement is met for the E2 reaction, and therefore even if you boil this thing with sodium ethoxide in ethanol for days, there will be no reaction, no E2 reaction. No E2 reaction will take place. This type of bridgehead compounds, bridged bicyclic compounds, where you have at the bridgehead the living group, they are very interesting substrates for the SN1 and SN2 reaction. You know, SN2 requires backside attack. As you can see, the backside is blocked by this cyclic structure, therefore this reaction is also not possible. SN2 is not also possible. Because the carbocation form cannot form at the bridgehead, E1 cannot happen, therefore consequently SN1 obviously out of the question. SN1 also cannot happen. Beta hydrogens are not in alignment with the carbon-chlorine bond, therefore E2 reaction does not happen. So if you boil this thing with sodium ethoxide in ethanol, no SN2, no E2. If you boil this thing with say silver nitrate and water, no SN1, because silver nitrate you are giving silver plus as a halophile which will take away the chlorine. This being a tertiary center, a carbocation should have formed, but it is not going to form because the tertiary carbocation cannot be planar. Therefore, SN1 and E1 is also not going to happen. So these are very interesting substrates which were first used by Paul Bartlett and his graduate student Lawrence Knox to study the SN1, SN2 reactions, and then it became the standard norm for testing the many hypotheses of SN1, SN2, E1, E2 mechanism by taking this type of bridgehead bicyclic systems which were supposed to resist all these mechanisms. If that mechanism is true, then this reaction will not take place, and it does not take place. So here is another example where we have a bridge type of system, but this time the leaving group is not on the bridgehead, on this carbon. So this is the alpha carbon. I have one beta hydrogen here, but that beta hydrogen, as you know, as this hydrogen is not coplanar with this chlorine, so therefore this hydrogen is definitely not coplanar with this OTS. And even if they were coplanar, I could not have formed the double bond here because that would have led to a double bond at the bridgehead, which again demands planarity. কিন্তু তুমি এখানে planarity দিতে পারবে না, এবং that is why the double bond as bridgehead is less stable. It does not form. But we have other options. এখানে এই বিটা হাইড্রোজেনটা আছে, এখানে এই বিটা কার্বনটা আছে. At this time we have couple of options. One is a deuterium, the other is a hydrogen. This compound has been specifically synthesized to test যে syn periplanar arrangement কি হতে পারে এবং সিন পেরিপ্লেনার অ্যারেঞ্জমেন্ট থেকে সিন পেরিপ্লেনার সিন এলিমিনেশন কি পসিবল? তো এখানে দেখো এই COTS and CD, those two bonds are like parallel to each other, but the COTS and the CH, the dihedral angle is 120 degrees. Therefore, it is the deuterium and the OTS which will be eliminated, not the hydrogen and OTS, because the hydrogen at beta carbon and the OTS at alpha carbon, they extend an angle of 120 degrees, and therefore, they are neither anti-periplanar nor they are uh, same periplanar. I have written anti, but that is not to say that it is anti-periplanar. When the dihedral angle is 180 degrees, then it is the anti-periplanar arrangement. Here the dihedral angle is only 120 degrees, but this dihedral angle is 0 degree, so this is a scene arrangement, and this is also scene periplanar, and therefore when we try to eliminate this, it is the deuterium which is lost, not the hydrogen. So in our alkene we don't expect any deuterium to be present, but if by any chance you would have eliminated this OTS and this hydrogen, which you cannot do because the scene periplanar and anti-periplanar arrangement is not there, you would have had, তুমি পেতে এইখানে একটা deuterium পেতে, you would have had a alkene with deuterium level, but that is not happening. Therefore we stand again corroborated যে যদি অ্যান্টি পেরিপ্লানার অ্যারেঞ্জমেন্ট না আসতে পারে তো সিন পেরিপ্লানার করবে, কিন্তু সিন পেরিপ্লানার যদি না হয় তাহলে E2 reaction হবে না। Finally, in this lecture, let me delve upon this particular example where we have a Z isomer of an alkene reacting a vinyl chloride reacting with sodium amide. When the Z isomer is reacting, the two hydrogen, the beta hydrogen and the alpha chlorine, they are anti-periplanar to each other, perfectly suited for E2 elimination. So amide minus is picking up this hydrogen and we are getting this carbon-carbon triple bond. When we have the E isomer in sodium amide, the alkyne is forming, but it is only a minor compound. On the other hand, we have a new product which was not there for the Z isomer, that is the alene system, that is a buta 1,2-diene, and that's the major product. Now this is interesting. Why is such a thing happening here? Let us check the relative orientation of the hydrogen and chlorine. They are anti-periplanar at the Z isomer, but in the E isomer they are syn periplanar. And because this carbon-carbon double bond is fixed, it cannot rotate, unlike these systems where you have possible rotation of the C alpha C beta, so that you can in most cases access the syn form or the anti form. But in this case there is this carbon-carbon double bond which prevents rotation. So this hydrogen and chlorine can never become anti unless you convert the E isomer into the Z isomer. But that is a separate set of chemical reactions. We are not interested in that right now. So when you have the E isomer, one possible reaction system that can take over is the syn elimination, which leads to the alkyne, but that's a minor thing. The other beta hydrogens that is being present in this substrate is the methyl hydrogens, and because this is a carbon-carbon bond which is actually essentially single bond, you can rotate it and access a conformation where one of the methyl hydrogen is placed anti-periplanar to the leaving group chlorine. And because anti-periplanar arrangements are favored and anti-elimination is favored compared to syn elimination, this elimination is the major elimination pathway leading to the formation of the alene system. As you can see, the methyl and hydrogen substituents at this carbon and the two hydrogens on this carbon, they will be perpendicular to each other, but this hydrogen, that methyl carbon, that vinyl carbon and chlorine, they are in the same plane and perfectly suited for the elimination reaction, maintaining the anti-periplanar relationship, and we are having this product where the alene is getting the majority share of the product composition. So this is how these reactions proceed, and the stereoselectivity is guided by the stereoelectronic requirement that you maintain either anti or if not possible syn periplanar relationship of the CH and the CX. I hope that you have understood the concepts that we have discussed here. I thank you for your patience and I will be seeing you in the next one.